and share screen. Um, um, the iterated integral of special forms. Oh, you can click this one here. The A. So from over rectangle. Okay, so you see here. Um, suppose you have a this special form is this one here. So the integron is a product of a function of one variable, f of x, g of y. Okay, let's see what we get here. So we compute this one, the A over the rectangle R. Well, that's the same as, let's see, this is x, gy. So suppose I do the expert. With expert, this is on C. My notation is slightly not standard, you see. So I usually put x equals something or y equals something here. Okay, so I'll write down the name of variable, so not to confuse the order of the integral. Okay, so the x dy. All right, so that means you integrate this first. Okay, respect to x. When you integrate respect to x, everything containing y is you think as a constant. As a constant, you can take this out. Okay, so what you get is y equals c, y equals d, e of x, because the constant is factored out. Constant factors also remain. Sorry, e of y. Okay, here this is the integration of one variables. Okay, you integrate f respect to x, right? And then plug in a and b for x. Of course, you get a number here, where the number is the integral. So you get this factors out also. This factors out. Okay, so at the end you have this one. So when you integrate a product, okay, so then that's okay. So it's like a product of integral of one variable. Okay, so that's the nice thing about integrations over rectangle. Right? Okay, so let me rewrite this down as a formula. It's just the integral from C to D d of y dy. Okay. Now the important thing is both whenever R is rectangle. If it's not rectangle, then you might have different things. So let's do some examples. Just take maybe one problem from the example. So textbook. All right, so let's see. Let's pick here, problem 15, for example. Okay, there's one. Okay, so this is a integral over rectangles. So here's the note. Let's take a note first. Here R is over rectangles. R, what is R? R is, so this is, okay. This one is, okay. So the X is between 0 and pi, and Y from 0 to 3. Okay, first, and the integrand is, sorry, cosine square of X. That is a product. So this is f of X equals e of Y. Okay, so this is the case when you can just compute the integral separately as one variable and then take the product out. Okay, so what we have is this. Okay, so this becomes cosine. This is the X. With X the 0 to pi, and then integral 0 to 3 y dy. Okay, so then let's compute this separately. One is anyone recall how to compute this one? How to deal with that square? Anyone? To get rid of the square, how would you do to get rid of the square? What to do in that case?
1 minus sin squared x.
All right, so that's correct. That's not a wrong step, but it won't help you because you still have sine square. So you're not getting rid of the square thing, just replacing cosine by sine. Here, double the angle. Or 1/2 1 plus cosine 2x. Okay, so then what you get is just 1/2. This x, this is cosine becomes sine. Okay, so 1 sine 2. So again, 0 pi. Okay, so plug in 0, that's 0, everything's 0. Plug in pi. If you plug in pi, sine is only here, so pi over 2. Okay, and second is, that's easy, y squared 0, 3. So that's plug in, so that's 9/2. Okay, so this gives you pi over 2 plus 9 over 2. Okay, so that's how you deal with the with this kind of integral. Let's go back to this one. Sometimes you just cannot separate the integral. For example, here, problem 9. Cannot be separated. It's not a product of one variable function. Okay, so this is the example. Okay. So this is example. You cannot separate function of x and function of y because somehow x and y is tied here. Okay, so in this case, you just have to compute this. All right. Let's see. Okay, so let's do this one here. Well, if we compute with x first, that would be no. Just compute with respect to y first. Okay. So in this case, you compute so derivative of sine xy respect to y, antiderivative sine become negative cosine. So first x, you can take x out, factors out. Why? Because x is constant with respect to y. Okay, so you can take x out, and sine become cosine, negative cosine, multiplied by the 1 over derivative, and 1 over this in respect to y is just x, so 1 over x. Okay. All right, if you plugged in 1, all right, so this cancel first. So we have this. Plug in 0 first. You plug in 0, this way, 0, 1. Plug in 1, uh, cosine 1. Oh, sorry, cosine 1. Okay, so this one is equal to 1 minus cosine x. Okay, so this is just x minus sine x. Y minus 1. Okay, then that's an example for this. Any questions? All right, if not, then let's continue with the next uh, all right, so let's see. Let's do this one first. Uh, the problem asks you to sketch the solid whose volume is the indicated iterated integral. Okay. All right. So, for example, um, this one here, 27. Okay. So here you have the according to this one, R is a 2 cross 0, 2. Okay. So you're looking at this one. That is our R. Okay. And on the top, the surface is this one here. So B, okay, and this is the paraboloid. Paraboloid. Okay. So this tells you that you compute the volume of paraboloids over this rectangle. So the sketch of the solids looks like this one. Okay. Uh, oh, okay. how the solid looks like. Well, it's not really precise, but this is what the integral tells you about. Okay, so it contains some geometric information. So you should be able to draw some pictures out of this way, these expressions. Okay, questions? Not then we'll continue with this one. Now, let's skip that first. All right, so let's do double integral over non-rectangular regions. Okay. All right, so let's just explain a couple of things here. All right, so we'll do some integrations over the region S now. S, which is not a rectangle. All right, so we not encircle, but we put S inside a rectangle R. Okay, and let's define. So you extend F is defined on S, but then you have to extend it so it's defined on R to allow yourself. Just put 0 here. Okay. So then that's what it means to have this integral. Okay. So that's what it means. Just rectangle, say, but you put 0 outside the region S. Okay. So how we compute this one? Okay. So double integrals over non-rectangular. Uh, First, it's what we call try to simple regions. Okay, as a simple region is uh, so set of xy such that the y is um, sorry, say this is phi1, phi2, and x between or set of xy. This one now is x is defined by alpha y, alpha 1, alpha 2, y, and y is there. See? So what's the similarity between 1 and 2 here? Mhm. So one variable is bounded by constant. Okay. Here x is bounded by constant a and b. Here y bounded by constant c and d. So and the other variable is bounded by two functions. Here y defined by sorry bounded by below by the function phi1, above from function by function phi2. Here x is defined by here, bounded by alpha 1, alpha 2. Okay, so the picture looks like this one here. So this is 1 and 2. So if 1 here you have x, y equals c2, y equals c1. Okay, and in this case, x equals alpha 2. Here you have x equals alpha 1. Okay. All right, and this has a name. This is what we call the y symbol, and this is an x symbol. Okay, so x symbol and y symbol. In here, okay. Okay, so this is an example of set which is neither x simple nor y simple. This, for example, here. Okay, so let me just even this one is yeah. So this one's neither x simple nor y simple. Okay, so if we deal with this one, well, we have to do something with this one. Okay. On the other hand, circle uh, would be simple. Say this uh, could be x simple or y simple. For example, if you deal with this, This is a y equals, and this y equals negative. So in this case, the y equals minus x squared and x between -1 and 1. Okay, so tells you that this is x simple. Sorry, y simple. One minus x squared. Okay, or you can do it the other way around. Okay. In this case, this would be x equals and x equals negative. So in this case, the region would be x is defined by x and y between -1 and 1. Okay, so then this tells you that this also x simple. Okay, but you have something that's either x simple nor y simple. Okay, so then let's do this one here. Okay, suppose this is a y simple. This is for y simple. Let me just point out and do a computation later. For y simple, you see this becomes here. This one here. Okay, with respect to y is the bounded by phi 1 and phi 2. Phi 1, phi 2. X defined by, bounded by a and b. So this is how you get it. And for something that x simple, you have this formula. Okay, so let me write down the end. So y is bounded by phi 1 and phi 2. X divided by a and b. Okay, so you have this phi 1. So it's phi 1, phi 2. Okay, this is dy. This is y equals. Okay, and the x between a and b. And for x simple region, yeah, a is, you have to do the one with this one first. X alpha 1 x equal alpha 2 dx and then 2 dy. So we'll continue with the example from this computation. Okay, and the idea is how to switch back and forth between order of the integrations. So, yeah. The problem is how to switch integration order. All right, so we'll continue this tomorrow. Any questions? All right, if not, then let's stop here. Stop the record.